I want to compute what is the probability that the crest amplitude C is greater than H. This probability, as an engineer, I always interpret probability as a ratio between what, in this case? Total number of waves in 0t on the denominator, and on the numerator I put number of waves in 0t with crest greater than H. That's what I was simply counting, okay? So I take my I recorded a time series of amplitude of length t. So I detect all my waves, basic values, and I know how to do that because I simply have to do zero crossing analysis. Okay? So I have what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 waves. Okay? And then basically, I fix a threshold H, and I'm gonna count what are the number of crests that are exceeding this amplitude, and basically I found 1, 2, and 3. So in this case, the probability that C is greater than H is basically equal to 3 over 11. Very easy. Okay. Now the question is, what we would like to do. Of course, you can see that in this case, if the threshold H is very large, if H is very, very large, the probability that C is greater than H is also equal to number of waves in 0t, number of H up crossings, crossing in 0t. Because how many up crossing I get? I get 1, 2, and 3. So this is also equal to 3 over 11. But this is only true for H larger than 1. Okay? And I'm going to show you now that an analytical solution for the probability of exceedance, of the crest or peak amplitude is still an unsolved problem, and it cannot, and only asymptotic results are available in the limit of H being much greater than 1. But as an engineer, what does it mean H much greater than 1? So we always have to compare to something, okay? So I mean here H divided by sigma to be larger than 1, okay? Where sigma is the standard deviation of our process. What I would like now to define, to introduce you to the Rice formula, which allow me to compute what is the expected numbers of average numbers of up crossings in an interval 0t. We can come up with an exact analytical solution for any random process, okay, which we then will particularize to Gaussian processes, and in this limit of very large amplitudes, which at the end of the day this is the range that we are interested in engineering, it will allow me to come up with a nice analytical formula for the probability of exceedance of the crest amplitude, okay? Which, I mean, it is used everywhere, especially in ocean engineering or in any type of extreme value analysis for prediction of extremes. Okay, it's going to lead us to the Rayleigh distribution. So what I'm going to do here, I have to introduce the let's be a little bit more formal. So let's given an interval 0t, in which I have time series 8 of t, which is random. Let me call let's define nw of t, the average number of waves in 0t, okay? And I'm going to show you that this average number of waves, they are also equal to the average number of zero crossings, okay? So, said that, now let me define you the expected number of up crossings with level h as times, let's call this average number of h up crossings per unit time. So this is basically a number divided by time. So if I want to get the average number of up crossings in 0t, I simply do exaph times t. Okay, this is basically average number of h up crossings in 0t. And again, here I exploit eta, basically, let's remember, is stationary. Okay, stationary. That's why now I can do this multiplication, because this average number does not depend upon time. Okay, so it becomes simply a multiplication. Okay, so this means that according to this definition, we can then say that the number of waves in t are equal to the expected number of up crossing, which level 0, so 0 up crossing, times t. This is average number of zero crossings per unit time. Okay? Of course, I can also define the expected number of crests, which are larger than h, ex of c, as the average number of crests with amplitude greater than h per unit time. Okay, this is and of course, no, so these are the number of crests. Okay, so, and of course, no, I can also define what, let's remember that this crest, you know, is the absolute maximum of a wave. Okay, so this is not an easy quantity to compute. Instead, what we can compute is the, again, let me give you an example. So these are basically, this is basically the crest and the trough. This is the crest, okay, which is also local maximum, but we also have local maxima, you see? So this is a local maximum. And of course we also have a local minima, but let's focus on the crest, okay? So you see that for this wave, we have one crest and basically two local maxima, okay? and an extra local, and more than one local maximum. Instead, for this other crest, we have one crest and one local maximum. Okay, so let's say that these are, we would call it spurious local maxima, that they are a problem. Now, of course, and so we can even talk about expected number of local maxima as the of amplitude h. So this is basically the expected number of local maxima with amplitude greater than h per unit time. And of course, we can also talk about, I already defined it before, expected number of crest with amplitude greater than h per unit time. Now, this, it's easy to compute. This, difficult. No solution. There is no exact analytical solution for this expectation. And of course, you understand what is the difficulty here, because characterizing in a probabilistic sense, what is a local maximum is pretty easy, because there is local quantities. Okay. However, now the crest is a global quantity, because besides being a local maximum, it has also to be the largest amplitude within this wave. And so imposing the condition that this amplitude here is going to be the largest one over an entire time segment of the wave, that is a global condition which is not easy to define probabilistically. However, as I show you before, and we will also prove it more rigorously, when h over sigma tend to infinity, and already when h over sigma is greater than h over sigma greater than 4, or already actually even greater than 2, if I remember correctly, is already a good approximation. We have that the expected number of crests are roughly equal to the expected number of local maxima greater than h, which are also equal to the expected number of upcrossing greater than h. Okay? So I can get an asymptotic results. So as long as h is sufficiently large, and I'm telling you that already for h over sigma greater than 2, for Gaussian processes we get a good approximation, we can basically compute the expected average of crest as those of local maxima or upcrossings. It turned out that the easy one to compute are upcrossings. But also the local maxima, there is also a very nice analytical formula which are valid for any random process, and and they're being developed by Rice. Okay, these are the famous Rice formulas. Okay, which have led to definition, a very nice analytical tool, and new ideas on how to perform this kind of computations. Okay, and that's what I'm going to show you now. So now let's compute what are the